Okay, so now we're going to go to independent events. We talked about independent events before, but now we're going to make it clear. So we did say already about the tossing 100 coins in a row, and we said that the coin has no memory, and so the probability that you get ahead on the next toss was still 1/2, and that was, we said that what happens on the 101st toss is independent of what happened before, and so we were using this idea of independence. Now we want to make it clear. We can make it clear because we use the idea now of conditional probability, and with that idea we can define independence clearly. Okay, independent events. At times, the probability of A given B, this should say equals the probability of A. For example, a fair coin is tossed twice. Find the probability that the second toss is head, and that the second toss is head given that the first toss is head. So this is kind of like the problem I explained before. So they're going to say that this is the conditional, right? Given that the first toss is head, what's the probability that the second is head, is the same as just that the second toss is head. So that's an example where this is equal to this. Anyway, they say that at times this is true. It's not always true, but sometimes it's true. In this case it's true because, like we said, the coin has no memory. But let's look at it again. If A and B are the events, A, that the second toss is ahead, and B, that the first toss is ahead, then this question becomes second toss is head given the first toss becomes A given B. Okay, so that then the sample space for this experiment is HH, HT, TH, TT. That means you can get head on the first, head on the second, head on the first, tails on the second, tails on the first, head on the second, and tails on tails. And the events A and B, the second toss is ahead is what? This has a second toss head, and this has a second toss head. And B, the first toss is ahead. This has a first toss head, and this has a first toss head. So these are A and B. And the event A intersect B is that, right? The intersection of these two is just HH. Okay? Now, what's the question we're going to want to ask? The probability, well, first that the probability of second toss is head. Okay, maybe we're going to do that one first. Since the coin is fair, we assume that the 4 sample points are equally likely. So the probability of A is 2 out of 4 because there's 2 in A. And so it's 2 out of 4. And the probability of B is also 2 out of 4. And the probability of A intersect B, is, where's A intersect B? Is 1/4, because there's only one case there. Thus the probability that the second toss is ahead is 1/2. Right? Probability of A is 1/2. And the probability that the second toss is ahead given that the first toss is ahead, that's the probability of A given B, is the probability of A intersect B, which we said is 1/4, divided by the probability of B. Remember the B here means that it's going to be B down here. So is 1/2. So we get 1/4 over 1/2, which is still 1/2. So A was 1/2, and A given B was 1/2. So like we said, sometimes the probability of A given B is the same as the probability of A. And that's in this case. So in that case, in the case where the probability of A given B is the same as the probability of A, then basically given B doesn't mean anything. It doesn't matter that we were given B. It doesn't affect the calculation. It's still just the probability of A. So that's what we mean by independent. So we say that A and B are independent if the probability of A given B is just the probability of A. So given B doesn't matter. So let's read what they say. In other words, the probability of A is unaffected by the additional knowledge that B occurs. Intuitively, this tells us that the two events are independent. That is, they do not influence the probabilities of one another. The result is not expected. It states that the coin has no memory. When the second toss is made, the coin does not remember what happened on the first toss. Thus, the chances of a head on the second toss will be 1/2 regardless of the outcome of the first toss. Let us pursue these ideas in more detail. Suppose A and B are two events such that the probability of A given B equals the probability of A. So that's what we said just before. But remember, A given B is conditional probability, means this. I'm just taking this and putting its definition here. So we get this. Now, of course, we can bring this up to here, which they do here. And this is, so if this is true, means if they're independent, we get here, we get here. So actually, this is what we usually use as the definition of independence, although this is fine also. But usually this is what's used. So if you have independence, this equals this. Okay, so two events A and B are called independent if the probability of A intersect B equals the probability of A times the probability of B. This is kind of like the other rule that we had for union. Remember, for union we had A union B. Probability of A union B was probability of A. There were three terms there. And then in the special case where we had mutually exclusive, the last term disappeared. I hope you remember what I'm talking about. I don't want to go back and look at it. Here it's the same kind of thing. If you remember, just a little while ago we had an expression already for intersection, but it wasn't as simple as this one. It said the probability of A times the probability of B given A. So it wasn't as simple as this one. But this one is simple in the special case where they're independent. Just like in the other example for union, it was simpler in the special case of mutually exclusive. Here it's simpler for intersection in the special case of independence. So if you don't remember it, you have to go back and check it. So anyway, here's the definition of independence that we usually use, although this one is kind of more intuitively clear. Now it turns out that if A and B are independent, then this is true and this is true. So in other words, what they're saying is, if you start with this one, you can work and show this is also true. And of course, if you start with this one, you can work and show that this is true. So they're both the same. So if you have independence, it's this or this, doesn't matter. Okay, we just did this example 8 actually already. And here's a second example. So let's do this.